So in this video, I want to talk about question 4a from midterm number 2. And that was a pretty challenging question, so I want to spend some time on it. So the question is basically about what's the probability of rejecting a true null hypothesis that the mean of our observations is 0, depending on the sample size, right? And let's start with just a single observation, right? So a single x. So what's the probability that this single x would lead us to reject the null hypothesis, the true null hypothesis, that the mean of the distribution is 0, right? So here's what the normal distribution looks like, right? And what we're asking is, like, what is the x that would lead us to reject the null hypothesis that the distribution is 0? So intuitively, it would be an x that's far enough away from 0 compared to sigma that we just say it's implausible that the mean is actually 0. So let's say that we know that the sigma squared is 1 and the mean is 0. We assume that's the null hypothesis, and then we get an x that's equal to 1 billion. That's inconsistent with the mean being 0 and the standard deviation being 1. Okay, so that would lead us to reject the null hypothesis. So how often would it happen if the null hypothesis actually happens to be true? So this is our normal distribution. So this sigma is about here, and here we assume for the moment that we actually know sigma, right? So clearly, if we get an observation that's close to 0, that would not lead us to reject the null hypothesis. On the other hand, let's say that we get an observation that's over here. So let's say that you'd get a value smaller than this observation more than 98% of the time, right? So that means that you'd get something more extreme. So if this way is like 98% of the time, this is the observation here, right? So you'd get something more extreme 2% of the time over here and 2% of the time over here, so just 4% of the time. So if you get something that's more extreme just 4% of the time, then the p-value is under 5, so you'll reject the null hypothesis. Okay. So if you get an observation right here where 97.5% of the observations under the null hypothesis would be below this observation, then the p-value would be exactly 5%, right? Because there is 2.5% going this way and 2.5% going that way. So what we need to do is we need to say, well, how often would it be that you'd get a value that's beyond this 97.5th percentile to the right or below this 2.5th percentile to the left? How often does it happen? Well, 5% of the time, right? Because this is what those percentiles mean, right? So like 2.5% of the time you'll get the value over here, and 2.5% of the time you'll get the value over here. 95% of the time you'll be getting a value over here. So 5% of the time you'll get a value, an observation that has a p-value associated with it that's less than 5%. So for n equals 1, you would be rejecting the null hypothesis 5% of the time. Now, if you have more than one observation, so then you would compute the x bar, and we know that the x bar is distributed like this. And again, you would compute the p-value, and the story is the same. So 5% of the time, assuming the null hypothesis is true, the p-value is going to be smaller than 5%. So the line kind of looks like this. So that is for a sample size starting with 1. If you want to be really strict about it, you would say, well, what about if the sample size is 0? Well, you would never reject the null hypothesis if the sample size was 0, right? So the graph technically, you could say, looks kind of like this, where it starts to be stable at 5%, starting with a sample size of 1. So things get a little bit more dicey when you don't assume that you know the sigma squared, right? So if you don't assume that you know the sigma squared, if you just have one observation, it cannot possibly provide you evidence against the null hypothesis. Why? Because let's say that you don't know the standard deviation, so you don't know this width here. So you get an observation, let's say over here, that's really far away from 0. Let's say this is like minus 1,000, minus 10,000, whatever. Does it provide evidence against the null hypothesis that the mean of all the observations would be 0? Well, no, like, sure, it's large, but it could be that the standard deviation is even larger, right? So it could be that the bell curve looks like this. And in that case, this is completely fine. It's not providing evidence against a null hypothesis. Now, once you get two observations, then you can start thinking. Because once you have two observations, you can compute the estimated standard deviation using our formula for the estimated standard deviation, right? So the estimated standard deviation would be just like the square root of xi minus x bar squared divided by n minus 1, or n, right? And then that would be the estimate, and then you would say, well, like, compared to this quantity, how far away is the observation, right? So, and then if this is small, but the observation is really far away, or like the mean is really, or the observation is really far away from 0, you would say, well, then the p-value is small, okay? But that's just an issue of having to wait for n being equal to 2. Once n is equal to 2, it's exactly the same story as before, where the probability of getting a value that doesn't happen very often, doesn't happen 95% of the time, while the probability of getting this kind of value is just 5%. So the difference would just be that you would say, if you don't assume that you know the standard deviation, you would assume that you have a 0% chance of rejecting a null hypothesis with one observation, but then you have a 5% chance of rejecting the true null hypothesis starting at n equals 2. Now, one question that people asked was, well, but with the coin, it wasn't like that, right? And it's true that sometimes with the binomial distribution, it's not exactly like that. So when is it not like that with the binomial distribution? Well, let's say that you toss the coin twice, and you want to test the null hypothesis that the coin is fair. Well, there is no way that you could reject the null hypothesis that the coin is fair just by looking at two observations, because, well, the most extreme you could go is like 2 heads or 2 tails. The probability of 2 heads is 1/4. The probability of 2 tails is also 1/4. So that's more than 5%. So if you have just 2 observations, there's no chance at all that you could reject the null hypothesis. Even if you have 3 observations, you can't reject the null hypothesis. The probability of 3 tails is just 1/8, right? Which is, again, more than 5%. So sometimes, if you don't have enough observations, there's just no way that you could reject a null hypothesis. But with a normal distribution, where you could have observations that are really far away, potentially from your mean, even one observation, assuming that you know the standard deviation, is actually enough. Now, note that even with a coin, it's not as clear-cut. So let's say that you are testing the null hypothesis that the probability of heads is 99%. And you toss the coin, and you get tails. Under the null hypothesis, you would only get tails 1% of the time. That's under 5%. So even one toss of the coin, if you get tails, and your null hypothesis is that the probability of heads is really high, it's 99%, that would be enough to reject that null hypothesis.